So in the first video in this section, we learned a few new rules, the power rule, the coefficient rule, and the sum rule. And then in the last video, I worked through a couple of examples, but I didn't want to get into the really challenging ones here because I think these are hard enough that they kind of deserve their own video. So the purpose of this video is to work through 6 examples, C, D, E, F, G, and H. I purposely chose these examples to kind of illustrate some common misconceptions that arise when you're trying to use these new derivative rules. The first one, the derivative of 6 over x squared plus 2/3. When you see a problem like this, you'd probably think, well, I have two terms, so I'm going to break this up. I'm going to take the derivative of 6 divided by x squared, and then I'm going to add to that the derivative of 2/3. And if you're paying really good attention, you'd be like, wait, 2/3, isn't that just a constant? So its derivative is just 0? And I'd be like, yep, very good. You're like, all right, this example isn't too bad. Now I just take the derivative of 6 over x squared, which, let's see, I know the derivative of x squared is 2x, so shouldn't this be like 6 over 2x or something? Unfortunately, no. This is asking you to take the derivative of a quotient of two things, 6 divided by x squared. And we don't have any rules yet for taking derivatives of quotients. It's not as simple as just taking the derivative in the denominator here and leaving other stuff alone. The way this is currently written, we can't take its derivative. But if you're really good algebraically, you might be able to rewrite this in a form that we do know how to take the derivative of. Maybe at some point you learn that x to the negative 2 power is the same as 1 over x squared. That when you have negative exponents, that means, loosely speaking, you're going to take the reciprocal of that thing. So if you had 6 over x squared, you could rewrite that as 6 times x to the negative 2 power. It's not obvious at all that you'd want to rewrite this in this way. But if you were able to rewrite this in this way, note this is not calculus at all. This is just algebra, changing these parentheses to these parentheses. Then you'd be able to use calculus really well. We have a number, a coefficient, times some function x to the negative 2 power. So we take the 6 down in front and multiply that by the derivative of x to the negative 2 power. And we know how to take the derivative of x to the negative 2 power. All you got to do is use the power rule. But be careful. You take the exponent down in front, there's the negative 2, and then you subtract 1 from the exponent. Negative 2 minus 1 is not negative 1. Negative 2 minus 1 is negative 3. So the derivative of x to the negative 2 power is negative 2 times x to the negative 3 power. So the derivative of this entire expression would be negative 12x to the negative 3rd power. Or if you want, negative 12 divided by x cubed, because negative exponents mean take the reciprocal of, loosely speaking. We have our answer, but instead of just moving on, I want you to kind of go back to the start and look at that. You probably would not have predicted that the derivative of 6 over x squared is negative 12 over x cubed. And the reason why, if you're like 99% of students, is because you would have tried to use the power rule kind of inside of a fraction. And it turns out that you can't do that. You have to be really careful with these new rules we have. Equally as challenging as learning how to use them is learning when you cannot use them, as you see in this example here. So that's another plug for going through these steps really carefully and writing out what you're doing in each of the different steps. Because if you don't, you'll find yourself making mistakes by applying rules in places that they don't apply. So I guess the purpose of C was it's sort of a cautionary example. D is very different. You look at D and you're like, I don't know how to do this. You haven't taught me anything about square root signs. And that's true. However, much like x to the negative 2 is an algebraic fact that's really useful to know for calculus, x to the 1/2 power is equal to the square root of x. Being able to rewrite expressions that are not conducive to our derivative rules in forms that are conducive to our derivative rules is a really useful talent for a calculus class. So what you'll want to do here is think about this as the derivative of negative 46x to the 1/2 power plus the square root of 3. And you might be like, wait, don't you want to make this 3 to the 1/2 power also? No, and I'll show you why. Now that I've rewritten the problem in a way that's more conducive to my rules, let me apply some of my rules. I have the derivative of a sum of two things. So I can take the derivative of the first thing, negative 46x to the 1/2, and then add to that the derivative of the second thing, the square root of 3. For the first thing, I have a coefficient, negative 46, times x to the 1/2 power. So I can take that negative 46 out in front of the derivative, and I got negative 46 times the derivative of x to the 1/2 power. What about the derivative of the square root of 3? Why didn't I rewrite this in a different form? Because this is a constant. The square root of 3 is just a number. I know it doesn't look like a constant. It looks like some function, but there's no variable in here. There's no x. This is just some number. Put it into your calculator if you want to figure out what number it's equal to. It's like 1.7 something, I think. The derivative of any constant, any number, is just 0. So we don't have to rewrite this in some other form. Since it's a constant, its derivative just goes away. It's done. So all we have to do is finish up the derivative for this first term, and we're done. We still got this negative 46, and we have to multiply that by the derivative of x to the 1/2 power. What's the derivative of x to the 1/2 power? You haven't seen fractional exponents yet, but when we learned our power rule way back here, it didn't say anything about this n having to be a whole number. This rule holds up for any value of n, other than n equals 0 technically, but don't worry about that. So I can use this rule when n equals 1/2. How would that work? Well, let's see. I take the 1/2 down in front. The old exponent always ends up in front. And then I would have x raised up to some power. And that power would be whatever the old exponent was minus 1. So what is 1/2 minus 1? Well, 1/2 minus 1 is just negative 1/2, right? 1/2 minus 1 is the same as 1/2 minus 2/2, which is 1 minus 2, or negative 1 over 2. 1 less than 1/2 is negative 1/2, so the derivative of x to the 1/2 power is 1/2 x to the negative 1/2 power. There's no d over dx symbols left, so we're done here. Although you could simplify this a little bit. You could say 1/2 times negative 46 is negative 23. So I have negative 23 x to the negative 1/2 power. You don't have to go any further than this, but it's worth pointing out that negative exponents just mean take the reciprocal of. So I could rewrite this as negative 23 divided by x to the 1/2 power. And because x to the 1/2 power just means the square root of x, I could rewrite this as negative 23 divided by the square root of x. You don't have to do this. Any of these three answers are totally fine. However, if you get in the habit of recognizing that all three of these things are equivalent, it might help you turn questions like this into questions like this that work better with our derivative rules. For the sake of taking derivatives, we prefer exponent form to radical form. But some books might tell you that if the question's given in radical form, the answer should also be given in radical form, which is an argument for making this the final answer. But I could tell you in our class, any of these three are perfectly good. Let's do another one, E here. E is meant to be the expert version of the things that you learned in C and D. There shouldn't be anything new in E. In E, we have three different terms. So we want to take the derivative of 5 over x cubed, and then we want to subtract the derivative of the cubed root of x to the 5th power divided by 7. And then we want to add to that the derivative of the square root of 3/2 minus 5 to the 10th power. Wow, this looks really hard. I think what you'll see is it's really not that bad if you can rewrite things in exponent notation. This first term is really just asking me the derivative of 5 times x to the negative 3rd power. This second term is really just asking me for the derivative of 1/7 times, instead of dividing by 7, x raised up to the 5/3 power, instead of the cubed root of x to the 5th. This 3 kind of goes here, and this 5 kind of goes here. And then this last one, you're like, oh, how are you going to rewrite that algebraically? I'm not going to bother. I'm going to leave it exactly how it looks. You might think you have to change this into a square root sign. You might see this 10th power and think the power rule, but you don't want to do any of that. This is just a number. I don't know what number it is, but the letter x, my variable in this problem, doesn't show up anywhere in here. You pull out your calculator, it'll tell you what number this is equal to. And I'm sure you don't care, but I don't like that what's underneath the radical is a negative number here. Doesn't change anything, but maybe I'm going to pretend this was a plus here just for my own purposes. Don't worry about that. The hardest part of this calculus problem is the algebra. It's rewriting this stuff like this. If you can rewrite it like this, you're probably going to end up getting things right. The derivative of 5x to the negative 3rd power, the 5 is just going to hang out, and then I'm going to multiply that by the derivative of x to the negative 3rd power, which is negative 3x to the negative 4th. Note that this is 2 lines of work. I could show the 5 out in front times the derivative of x to the negative third, and then in the next line, take the derivative of x to the negative third. But maybe at this point in the video, you're expert enough that you can do both of those in a single step. What about this term? I got minus 1/7 times the derivative of x to the 5/3 power. The derivative of x to the 5/3 power, you take the old exponent, 5/3, and you bring it out in front, and then you subtract 1 to figure out the new exponent. 5/3 minus 1 is the same as 5/3 minus 3/3, which is 2/3. And then the derivative of this huge mess, again, it's like a trick question. This looks really ugly, but you don't have to worry about it. It's just a constant. The derivative of a constant is just 0. Could leave things like this, but it's a good idea to simplify a little bit. 5 times negative 3 is negative 15. So I got negative 15 x to the negative fourth, and negative 1/7 times 5/3. You multiply fractions straight across, and you get negative 5/21 times x to the 2/3 power. This is a great answer for our class. You can stop right here. But some books would say that if the question didn't have negative exponents, the answer shouldn't have negative exponents. And if the question didn't have fractional exponents and instead was written in radical form, the answer shouldn't have fractional exponents. So if you really wanted to, I don't need you to, you could rewrite this as negative 15 divided by x to the positive fourth power minus 5/21 times the cubed root of x squared. Again, I don't need you to do that, but I'm going to demonstrate it because the more you see going from this form to this form, the better you'll be at taking something that kind of looks like this, like the original question, and changing it into something that looks like this, which is what you needed to do to take this derivative. 3 more problems, and I think all 3 of them are kind of the cautionary tale types, the types that look like they'd work a certain way, but they don't. The derivative of, again, we got 3 terms, so think about this like we have 3 different derivatives to take. X to the 5th and x to the 30th. Oh, I'm good with those. That's 5x to the 4th, and that's 30x to the 29th. No. The derivative of a quotient is not the same as the quotient of the derivatives. You can't just take the derivative of the top and the bottom. What you have to do is rewrite this so that it's in a form that's conducive to our rules. Same with over here. I know you could take the derivative of the square root of x, and I know you could take the derivative of x, but it's not enough to just take those 2 derivatives individually and multiply your answers together. We have to rewrite this so that it fits the rules that we have. Often the hardest part of calculus is algebra. Let me do the algebra for you. X to the 5th divided by x to the 30th is the same as 1 over x to the 25th power. Kind of think about it like you're canceling 5 of these x's with 5 of these x's. X times the square root of x is the same as x times x to the 1/2 power, because the square root of x is the same as x to the 1/2. And then 9 times 2, if you want, you could write that as 18 because it's easy to do, but really you don't even have to. This is a constant, and the derivative of any constant is just equal to 0. You're like, all right, cool, now I can use the rules that you've taught me to figure out this derivative. No, this still is not in a form conducive to our rules. To take the derivative of 1 over x to the 25th power, you want to rewrite that as x to the negative 25th power. To take the derivative of x times x to the 1/2, you want to rewrite that as x to the 3/2 power, because maybe at some point you learn the rule that when you're multiplying together 2 different exponents with the same base, what you do is you add up those exponents. X to the 5th power times x to the 3rd power is x to the 8th power. And kind of using the same logic, x to the 1st power times x to the 1/2 power is x raised up to whatever 1 plus 1/2 is equal to. 1/2 is just 3/2. And then I'll leave this 18 for now because I haven't done any calculus yet, but quickly you'll see that it goes away. I've done 2 lines and a fair amount of work just rewriting the problem, not doing any calculus at all, but I'm now to the stage where the problem looks like something that I can attack. What I want to do is take the derivative of each of the terms individually. You could write that in a line if you want, but I bet you're at the point where we can just say, well, the derivative of the first term is negative 25x to the negative 26th power. The derivative of the second term is negative 3/2 x to the 1/2 power. 3/2 comes down in front. 3/2 minus 1 is 1/2. And then the derivative of this 18 is just 0, which really you don't even have to write. This would be a perfectly acceptable answer in our class. And if you can follow all that steps, that's pretty good. This is getting to kind of the expert level problems for this section. Again, you don't have to do this, but I should at least point out that this is equal to negative 25 divided by x to the 26th power minus 3 square root of x divided by 2. You don't have to go from here to here, but it never hurts to see that this is equal to this. Just reconcile these two things in your head and then maybe move on. Let's do another problem. The derivative of 2x plus 1 squared. Oh, that looks super easy, right? I mean, I can just use a power rule or something. I know the derivative of 2x plus 1, and maybe I bring this 2 down in front. Nah, it's not that easy. This isn't x squared. It's 2x plus 1 squared. And dealing with 2x plus 1 squared is not a topic for this section. It's a really hard topic, in fact. And you're like, all right, stop telling me what I can't do. Tell me what I can do. Well, maybe you can rewrite 2x plus 1 squared, right? 2x plus 1 squared just means 2x plus 1 times 2x plus 1. And you're like, okay, so make this the derivative of 2x plus 1 times 2x plus 1? No, because that's not any easier to take derivatives of either. But maybe what you could do is FOIL this out and get 4x squared plus 4x plus 1. Don't think about the derivative of 2x plus 1 squared. Instead, think about the derivative of 4x squared plus 4x plus 1. And all of a sudden, it becomes a really easy problem. Don't mind my dog crying. He really wants me to play with them. In fact, this is so easy that you can probably do it without even showing your work, right? We want to take the derivative of each of the 3 terms individually. For the first term, pull the 4 out in front and take the derivative of x squared. If you can see how that's going to turn into 8x, that's awesome. For the second term, take the derivative of 4x, pull the 4 out in front. The derivative of x is just 1. 4 times 1 just gives me 4. The derivative of the 1 is just a 0. My answer is 8x plus 4. The calculus here is super easy relative to these other problems that we've done, but the algebra is not. Because what happens on problems like this is people try to use rules. I mean, think about how you would attack this if I didn't show you. I don't know, maybe you would have called it 2 times 2x plus 1 to the first power or something. But that's not the same as the answer ended up being. You got to be really careful not to apply rules that don't apply in calculus. Last one, but before I get to the last one, I want to make the point that you should not be expected to be able to get this answer until you've seen somebody get this answer, right? Don't be too hard on yourself. If you were like, yeah, I wouldn't have figured that out. You're not supposed to. That's the purpose of watching this video, right? But now that you've seen it, when you see a similar problem, you'll be like, oh yeah, I know what not to do. And I also know what to do, and I can get this answer. Anyways, the derivative of 2x plus 1 squared over x. You're like, well, I just learned the derivative of 2x plus 1 squared is 8x plus 4, and I know the derivative of x is just 1, so I don't know, maybe it's the same answer? No, it's certainly not the same answer. The derivative of a quotient is not the quotient of the derivatives. You can't just take the derivative of the top and the bottom. You have to rewrite this in a form so that it fits your rules. You got to do the algebra before you do the calculus. So let's do the algebra. Up on the top, we've already seen that 2x plus 1 squared is 4x squared plus 4x plus 1. So what I want to do is divide all that stuff by x. A useful algebraic technique is when your numerator is the sum of a bunch of different terms, you can take each term in the numerator and divide it by the denominator. What I'm saying is 4x squared plus 4x plus 1 over x is the same as 4x squared over x plus 4x over x plus 1 over x. If you have a hard time going from this line to this line, think about working backwards. If I started you out with this, maybe you'd recognize that you have a common denominator, so you can add up the numerators, which would take you up here. You're like, all right, I guess I kind of see that those are equal, but I still don't see how I'm going to do calculus on this. Well, we need to simplify this. One more step of algebra. 4x squared over x is the same as just 4x. I can cancel this x with one of these x's. 4x over x is just 4. Cancel this x and this x. What about 1 over x? There's nothing that I can cancel, but it's not in a good form to take the derivative of. Oh, I know what I can do. I can think about this as 1 over x to the first power, which I can rewrite as x to the negative first power. It's almost like a puzzle, right? You get this problem and you don't know where to go, but you do know that you only have a few different tools. And so what you got to do is rewrite this so that it fits the tools that you have. And for most students, that's what's hard about this section. It's not taking these derivatives. Once you get to this stage, you're probably going to do okay. The derivative of 4x is just 4 because I take the 4 out in front, and then the derivative of x is just equal to 1. The derivative of the 4 is just 0 because 4 is just a constant. And the derivative of x to the negative 1 power, I bring the negative 1 down in front, and then I subtract 1 from the exponent, so I get negative 1x to the negative 2 power. 4 plus 0 is just 4, so I could rewrite this as 4 minus x to the negative 2, which is perfectly acceptable for our class. But FYI, this can be rewritten as 4 minus 1 over x squared. Either of these are good for your final answer, and I think this is where I want to end this video. And I'm going to go take my dog to the park so he stops crying.